Towards the end of the last video, we were doing derivation for the crank effort, that is determining the force at the crank pin due to the net piston thrust. So we did a velocity triangle for that. So we saw that Ft into R, the torque will be equal to Ft into R, and also if you take the thrust along the connecting rod and multiply the normal distance, it is the shortest distance of connecting rod from crank center, that is this quantity OP. So if you multiply the force along the connecting rod and multiply with OP, we will also again get the torque. So that's how we can equate these quantities. OP multiplied by FC is equal to Ft into R. Ft is the quantity we are interested in. So from this triangle, we saw that the angle OAD is equal to theta plus beta from the law of exterior angle, and therefore OP will be equal to OA sine beta plus theta, that is angle OAD. This OA quantity is R sine beta plus theta. So substituting in this relation, we get Ft into R is equal to Fc into R sine theta plus beta. Now from our earlier derivation of Fc, we know that Fc is equal to F divided by cos beta, that is the net piston driving force F, and R gets cancelled both sides. So Ft is equal to F sine theta plus beta divided by cos beta. So this is the crank effort. If you multiply the crank effort by radius, then you get the torque on the crank, which is the quantity of interest in design, because this will be the final output from the engine or input to the compressor. Now the further quantity of interest 5 is thrust on the crank bearing, that is the bearing at the crank center. So in this velocity diagram that we saw earlier, this is the crank center O. We want to find out the thrust at O, this place. So in this diagram, Ft is a force normal to the crankshaft, that is along tangent to the crankshaft. Similarly, there will be a component along the radius of the crankshaft, that is Fr. So this component will be normal to the crank. So if you draw a crank like this, there will be a compressive thrust inside the crank. There will be a normal component Fr and a tangential component Ft. The expression for Ft we just derived here, and that will create torque on the crank, and the Fr, the component Fr will create a thrust on crankshaft bearing. So this quantity is important because we want to calculate the normal thrust on the bearing, and we want to calculate the frictional loss. So, and also for design of the bearing, this load is important to calculate. So if you consider the same velocity diagram, the force balance diagram at the pin, crank pin. So in the crank pin, Fc is coming in this direction, that is force from the connecting rod. This is the crank, and Fc makes an angle theta plus beta with respect to cab. The component of Fc along the crank will be Fc multiplied by cosine of angle between the two lines. So cosine of theta plus beta. So this will be equal to the Fr, the force along the crank. So Fr is equal to Fc cos theta plus theta. We know the value for Fc, that is F, the piston driving force, divided by cos beta, and here the quantity is cos theta plus beta. So Fr, the radial force along the crank, or the thrust on crankshaft bearing, is equal to F cos beta multiplied by cos theta plus beta. Now we will do a simple derivation of the turning moment of the crankshaft from the trigonometry of the slider crank geometry. Earlier we saw that Ft, the crank upper, it is equal to F cos beta divided by multiplied by sin theta plus beta. So it can be determined like this. But if you don't want to calculate the sine or cosine functions, you can also do a derivation from simple trigonometry. So this is a slider crank mechanism. This is the cranking crank center. This is the crank circle. So the force along the piston is F. This is along the connecting rod Fc, and at the crank the normal force is Ft. It is the perpendicular to the crankshaft, and along the crankshaft is Fr. We have derived the expression for these two also. Now if you do these two functions, that is extend the line, the connecting rod line along the connecting rod direction, then it will intersect somewhere the vertical position. That position will term as D. And if you drop the perpendicular from this the crank center O on this line AD, D is the point where on this line AD, this point will term as P, and the angle OAD is equal to beta plus theta that we saw earlier. Beta and theta is some of the internal triangles. So we know this quantity OD, and we will do a derivation where we will eliminate the use of theta and beta. So I'll just magnify this triangle for getting the better clarity. This is a vertical line from O. This is the point D. This is a perpendicular drawn from O, the point P. This is the point A, which is crank pin. And this angle OAD is beta plus theta, and the length O is R. That is radius of the crank, as you can see from this diagram, O to A. So from this triangle we get a relation that R sine beta plus theta will be equal to OD cosine of this angle. So now this is a horizontal axis, this is a connecting rod. The connecting rod makes an angle beta here, and this is a straight line. BAD is a straight line. So, and since this angle BOD is 90 degree, so angle this angle will be 90 minus beta. Now since this angle is 90 minus beta from this right triangle OBD, then we can determine this angle also. So this is a right angle here in the triangle OPD. Since this angle is 90 minus beta, this angle will be beta. So the length OD cos beta will be equal to length OP. OP is equal to OD cos beta. So R sin beta plus theta will be equal to OD cos beta. We are doing the expression for OP. So OP is also R cos beta plus theta and also OD cos beta. Now we substitute this value sin beta plus theta in the value for Ft. So Ft will be equal to F sin beta plus theta is OD by R cos beta and in denominator also we have cos beta here. The cos beta and cos beta will get cancelled out. Ft into r is give Ft into r is equal to F into OD. So the turning moment on crankshaft can be determined by multiplying the force on the piston F with distance OD, that is the vertical line intersecting the extension of the connecting rod. So it's a simple expression where you don't need trigonometric quantities. You draw a vertical line from the crank, vertical to the horizontal axis, and you extend the connecting rod wherever they intersect. That point is D. Calculate D and multiply with F, and you can get the turning moment. Now we will take a numerical problem on the subject of piston force analysis. So crank is given at the 90-degree position. So theta is given to be 90 degree, and this is the piston, the connecting rod BA, and the crank center O. This is the angle beta. So theta is given as 90 degree. The length of the connecting rod is given as 2 meter. The radius of the crank is given as 1 meter. So the N, which is ratio of L and L by R, becomes 2, and the mass of piston is given as 1 kg. The omega of the angular velocity of crank is given as 10 radian per second, and the question is to find the turning moment for this position. That means theta is equal to 90 degrees. So we will go on solving this problem. For determining the turning moment, we need the effective force F on the piston. So F is a summation of Fp, and in the problem Fp is also given. So Fp is equal to 100 Newton given, that is a gas pressure. So we have to calculate F first. For that we need the inertial force of the piston, that is Fi. So Fi is given as m r omega square cos theta plus cos 2 theta by n. That we recall from our formula that we just derived. M we substitute value, mass of the piston is 1 kg, radius of crank is 1 meter, omega is 10, so 10 square is 100, and theta is 90 degree, so cos 90 degree plus cos 180 degree, that is 2 theta divided by n. N is 2 in this problem. So on solving this, you get cos 90 degree is 0, cos 180 degree is minus 1, so this becomes minus half, so Fi becomes minus 50 Newton. So the nature of Fi is such that it is away from the crank pin because it is negative. That's why it's away from crank center O. Now the net force, net piston driving force is equal to Fp plus Fi. We are neglecting the friction because that is not given here, and the gravity, that is also not given here. Only two forces are there, Fp, that is 100 Newton, minus Fi, that is inertial force, plus Fi, that is inertial force, that is minus 50 Newton. So the net piston driving force is 50 Newton. So the next step is to calculate the turning moment. For turning moment, we need the crank effort. Crank effort is the tangential force at the piston. It is Ft, crank effort Ft. So the formula for Ft is, as we saw in our derivation just now, F by cos beta sine theta plus beta. Now for that we have to calculate the angle beta. Theta we already know, it is 90 degrees. here. So for calculating the beta, we have our original identity in the crankshaft, that C you say, it is Y. So AC is equal to R sine theta from this triangle, triangle OAC, and Y is also equal to AB, that is L sine beta in this triangle CBA. So we get R sine theta is equal to L sine beta. R is 1, sine theta is 90 degree, sine theta also becomes 1, equal to L, value of L is 2, sine beta. So sine beta becomes 1 into 1 by 2, that is equal to half. If you do sine inverse of half, you get beta is equal to 30 degree. So beta is 30 degree. Now we substitute these values here for ft in the expression for ft, that is f by cos 30 degree sine 90 plus 30 degree. So we know the identity that sine 90 plus theta is equal to cos theta. So substituting here, you get f cos 30 divided by cos 30. This gets cancelled out. Turning force Ft is equal to F here. So the turning moment, that is Ft into R, that becomes F into R. F is known as 50 towards the center O, crank center O, and R is 1. So the turning moment is 50 Newton meter. This is our answer. Now in the same problem, we can also determine a quick solution for the turning moment if you know the F only. Just now we saw that if you draw a vertical line from O and you extend the connecting rod, you get the intersection point D, and you multiply the length OD with the F, you can get the turning moment. So in the present case, the vertical line from OA is same as D. So the point A and D are same, and this length is R and this force is F. So finally you can simply get the turning moment is equal to F into the length OD. OD is equal to OA in this case is equal to R. So turning moment is F into R, simply. Now we come to the another important topic in the theory of machine, chapter 1, mechanisms, that is the third section, velocity analysis in 4-bar mechanism. In this topic we will study velocity diagrams from which we can determine the velocity of various points on rigid links of a mechanism. So before going to the mechanism, we will consider the velocity analysis of a link in general, and then we will extend the principles to a mechanism. So the procedure here is more of graphical instead of analytical construction of velocity triangles. So this we need to know because many questions are asked from this topic. So for a link, you consider a link in space, say AB, and the point A and B are having some velocity. Let's say VA is the velocity of point A, VB is the velocity of point B, and if you fix one link, let's say if you fix B, then the link A will appear to be rotating about point B. Similarly, if you fix the link for point A, the link will be AB will be appear to rotate about point A. The angular velocity of rotation will be termed as omega. And let's say C is any point any general point on the link. So this is a general mechanism moving in space. Let's say there is some point O which is fixed, some fixed point O which acts as a origin or coordinate system, whatever you may call it, and the link is general link where A and B are moving in space with respective velocity VA and VB. So we can draw the velocity of A with respect to all the velocities, because O is fixed. All velocities are with respect to O, the fixed position. So we can draw a velocity triangle in a way that the velocity of A relative to O will be drawn like this. The vector VA, just we have replicated the vector VA here. So this is velocity of A, velocity of point A with respect to O. This is fixed point VA. The magnitude is same as the magnitude of vector is same as the magnitude of velocity VA, and direction is also same. Now we can also determine likewise for the point B also. We know VB. So let's say this is a line, this is a vector VB. So this point will term as small b. All velocities will term as in small letters, and actual link in big capital letter. Actual link position, spatial position, coordinates in space where the position is, that will be in capital letter. So in this velocity diagram you see small a small b is the velocity of b relative to O, that is fixed link. This is VA, velocity of A relative to O. Then if you connect these two lines B and A, then this will give you velocity of A relative to B. VAB, velocity of A relative to the B. This will give you the relative velocity. Like this, you can construct the velocity triangle. And for finding any point velocity, like there is any point C on the link, then you can divide this length VAB in the same ratio in which C is dividing the link AB. And then you can draw a vector from origin, and you can get any general velocity of VC, any general velocity of any general point, VC. So I'll write these things for you. VAB, small v, is velocity of A relative to B, point A relative to B, and this will be useful in determining omega. So if you fix the link B, then you will see the A will be rotating about point B. So the direction of VAB will be such that it is perpendicular to link AB. So VAB will be perpendicular to length AB, because they can't be in contraction along the length AB. So that's why the velocity has to be tangential. Now this property can help us to find out omega, that is the angular velocity of link AB, omega, that can be determined by VAB divided by AB, the length. This is identity omega is equal to V by R. Now the property that the VAB will be perpendicular to length AB, this is a very important property which will help us to calculate velocity triangle in case only direction of one velocity of one point is known and magnitude plus direction of another point on the link is known. So for point, let's say for this example, A and B can be any general point. Let's say for this example, for A, VA magnitude and direction both are known, and for point B only, for VB only direction is known, the magnitude is not known. Then also we can construct the velocity triangle. So you have the point origin A, you draw the line VA, the velocity of A relative to fixed. Now you know the direction of velocity B, so you can draw a general line, let's say this dotted line. Okay. So first step, draw vector VA for which both magnitude and directions are known. Second step, draw a line in direction of VB. So since direction is known, we can draw this line. And the third step is that you know that VAB, the velocity of A respect to B, will be perpendicular to the link AB. So third step, draw a line passing through A and perpendicular to link AB. So you know, you see this direction AB, and the VAB is something like this. This is the direction of VAB. So we will draw a line such that it will pass through A and it will be perpendicular to the, this is A, this is B. So perpendicular to link AB and passing through the point A. So this line and this line will intersect somewhere. The point of intersection you can find B. So now this velocity becomes VB and this is VAB. So the fourth step, point of intersection of line in two, second step, and third step is B. This way you can find B and find the complete velocity triangle for any rigid link. Because there can't be any contraction or expansion along the length AB, so hence the velocity of A respect to B will be perpendicular to the length AB.